video. I'm Sir Olenjolaim from United Republic of Tanzania. I would like to welcome you into my YouTube channel that's called the Tanzania Online A-Level Secondary Schools in square brackets Olenjolaim M. Okay, so this is the abbreviations of the secondary. And this is the abbreviation of advanced level. So simply you can call it Tanzania Online Advanced Secondary School. Okay, so I will also take this moment to welcome you into this video, which is a sequence of series of videos, and this is, we call it a lecture or session or period 6 of gravitational mechanics. So I don't want to waste much of your time because I believe that you've been watching some other videos, but if you don't do that, please make sure that you watch some other lectures before you watch into this lecture, because this is the continuations of what I've already taught you in session 1 up to session 5. So this is just a continuation, that's why we call it session 6. So in case that you didn't do that, make sure that you go into this channel. You'll find all other previous lectures and use them, watch them several times as well as you can. And then I believe that you are serious enough right now. You've understood the focus and the visions of this channel, so you are ready to take or to progress where we ended in the previous lecture. So I would like to take this time and let us continue with your lecture. And the departments is advanced physics. The subject is advanced physics. This is for A-level, Form 5 and Form 6. The main topic is mechanics, and then the topic is gravitation. And this is for the Form 5, pre-Form 5, Form 5, OD, especially NTA level, OD, who are pursuing ordinary diploma for engineering. This is OD, so mostly we call it for NTA level 5, according to the NATE curriculums, NTA level 5. But also this material might be relevant for the students who are preparing for the final exams in the Form 60, and even somebody else who is learning about gravitational mechanics, because actually that is going to give you a lot of information about the gravitational mechanics. So in case that you maybe at the beginning, so later on in these sessions you want to offer your Thanksgiving, okay, you may use this telephone number so that you can be a part of driving these programs into millions of Tanzanians and even into millions of Africans and millions of the students or learners in the world. So let us continue with our sessions. I would like to start from the point of the quick review, and this quick review will be focusing on lecture or session 5 that we have learned. And mainly in lecture 5 we have learned about the planetary motion. Planetary motion. In this perspective, we have defined what is a planet. What is a planet? So when somebody asks you what is a planet, how many planets do you have? Okay, how many planets do you have? So we mentioned the 8 planets, right? That are the one of the contents of the solar system. So this is introductions of session 5 or lecture 5. But the main concentrations we focused on the satellite, we call it satellite motion. And these categories of satellite motions, we say that we have two types of satellites. We have natural satellites, and these are created by God, natural satellites. And also we have artificial satellites, right? Artificial satellites. Okay, so examples of natural satellites, for example, in the planet of the Earth, we have the moon. So the moon is the 1 of 14 of the natural satellites, one example of natural satellites. But also some other planets such as Mars has a number of satellites, number of natural satellites. The Jupiter, now the largest planet, it has 16 natural satellites. Okay, so we define what the means of natural satellites and also defines what the means of artificial satellites. For example, the moon is revolving around the Earth, right, in 27.3 days. So in case of artificial satellites, also we say that these are the man-made. So these are the man-made. When you hear about communication satellites, navigation satellites, weather predictions of weather forecasting satellites. So you'll find them in this category, and I mentioned the 8 types of artificial satellites and the ERT applications. So make sure that you go through this previous lecture. And hence we made the revisions because basically here we found the terms we call it orbital or orbital velocity. So we have derived the orbital velocity of 40 of the satellites, and hence we made just some few assumptions and we found about its orbital velocity. And also we learned about the periods of the satellite. Now what will be the periods, the formula to get the period. And hence I left two homeworks. The first homework is this: derive the formula of determining the periods of the satellites as a function of the density of S, radius of the S, universal gravitational constant, and height. And the second question was asking you to derive the formula that used to determine the height of 40, the height of the orbit where we can place a satellite, right? So I believe you did that homework. Hopefully, if you didn't do, make sure that you do it before you continue. I gave you two questions. I'll do correction for one question because the other ones was simple because it's just a matter of recalling one of the formula, and it was a formula of the period, right? The formula of the period, and then you make the height H as a subject. That's all. So you get the formula that you have been asked in the second question. For the third questions, let me just do corrections to encourage you. So the beginnings of today's sessions is corrections of homework. That was homework 5, and question number 1, you see it here. Derive the formula of determining the periods of the satellites as the functions of the density of the S. So when you say about, so there's the two ways that you can derive this formula. Basically, you can use the previous formula, and even you can use the formula that we have. Because we say that the first step, you have to recall that we say that we call velocity, right? Velocity is equal to change in distance over change in time. So for example, we say that we have time. This is equal to distance traveled over t over the velocity, right? And the distance for this stage, we say that because it's circular, its distance is equal to circumference of t over velocity, okay? And that velocity is orbital velocity. So we say that the circumference, or the time, which is period for this case, because the satellite will be revolving several times, so the period for this case will be equal to circumference, which is equal to 2 pi r, okay, 2 pi r, and then we have 40, the velocity. So we have orbital velocity, so this one called T velocity, orbital velocity. But the radius, this is equal to what? Is equal to the radius of the S plus the height divided by what? By orbital velocity. But also in previous derivation, second step, okay, so suppose that this is the first equation. The second step, I taught you how to derive the orbital velocity, okay? So you have just to recall. So orbital velocity in the previous case, for this case right now, we say that is equal to square root of the mass of the S times gravitational constant, radius of the S plus the height h. So then we say that the period of the satellite TS is equal to what? Is equal to 2 pi radius of the S plus what? Plus the height divided by orbital velocity. So orbital velocity, this is what? Mass of the S, gravitational constant, divided by what? Radius of the S plus the height h. Okay? So then this is a matter of division. So because we are going to divide, then we say that our period of the satellite S is equal to what? Is equal to twice pi radius of the S plus the height of the S divided by square root of what? Of mass of the S, gravitational constant, divided by the square root of what? Radius of the S plus the height h. So this one, this is over 1. So we say that the period of the satellite is equal to twice, then we have radius of the S plus 1 or plus h, and then s over 1. Then we say that if we change the operation from divisions to multiplication, then denominator become numerator, numerator become denominator. So this one we say that it is the square of 40, radius of the S plus h of 40, square root of 40, mass of the S times 40, gravitational constant. So then we say that the period of the S, the periods of the satellite will be twice pi, and then we say that the square root of 40, radius of the S plus the height h, and then we multiply by this expression, which is radius of the S plus the height of the S power t power 1. So we divide with what? Divide the square root of products of mass of the S and gravitational constant G. So we divide with the product of what? Square root of mass of the S times 40, gravitational constant. So period of the satellite is equal to what? So for this case is equal to twice pi, and then this one is radius of the S plus the height power a half, and then you have radius of the S plus the height h. So then we say that we divide with what? So this is power 1. Okay? So we divide with mass of the S times 40, gravitational constant. You can add the exponent because the base is the same, and then you get something. So then that's the second step. The second step that you have to take there is we have, because the questions ask us to derive the formula that determines the periods of the satellite, but are the functions of 40 of density of the S. So the third step, which will be the third step, yes, hopefully, yeah. So the third step we say that we have to recall the formula of 40 of density of 40, density of S. So the density of the S, which is this the notation, we used to find by using the mass of the S over volume of the S. So the mass of the S, so it means that now mass of the S for this case is equal to density of the S times the volume of the S. Okay, the S is a sphere, so its volume is 4 over 3 pi r radius of the S cube. Right? So if that's the case, now we say that if that the density of the S, then we say that that's the mass of the S. So suppose that if we express this one, period of the satellite is equal to twice pi, then we have radius of the S plus the height was 3 over 2, means a half plus 1. Then we say that divided by square root or mass of the S. So we divide with what? So let's say I can write like this way. So divided by square root of what? Mass of the S, gravitational constant. So suppose that this is equation 1 or equation 3. Equation 3, because this is equation 1 and this is equation 2. So equation 3. So and this one is equation 4. So now the first step, we say that substitute equation 4 into equation 3. Okay? So how do we substitute it? We say that in case you have any question, don't hesitate yourself to use the comment sections, ask your questions. So we say that if we substitute now, we have the period of the satellite is equal to twice pi radius of the S plus the height h power 3 over 2. 3 over 2. And then we say that divided, so we have divide, we short it, mass of the S times universal gravitational constant. But right now, so we have to write the universal gravitational constant. Mass of the S is 4/3 then by R cubic times density of the S. Right? So if that's the case now, we can have a decision of rewriting it properly. So period of the satellite is equal to what? So you can leave the way it is. Maybe you can write it properly, it's fine. So we can say that this is twice pi, and then we say that it's the square root of what? It's the square root of radius of the S plus the height, but this one is cubic because a half is the meaning of this is square root, divided by what? Divided by 4/3 as constant times universal gravitational constant times pi times radius of the S cube, and then times density of the S. So this is the formula you are required to derive as a good student. Okay, so that's the formula, right? So I think that you enjoy it and keep on enjoying it. Okay, so that's all about the first question. So let us proceed and let us continue with today's lecture. So today I'm going to teach you about the orbit of artificial satellites. I told you that artificial satellites are very important in human life, in the planet, in today's planet, so in today's life and even in the future generation. So the content, the main focus of this lecture today is about a terminology that we have touched it and even discussing it in some of the previous lecture. And these terms or this vocabulary we call it orbit. Okay? So we are going to focus on the orbit of what? Of the satellites. 4 hours. 4 hours. So those are the 4 conditions necessary to place artificial satellites into parking orbit. You can find some other conditions, but not limited. That's your responsibility, but I've taught you at least the 4 conditions which are important for you in your life. So in case that maybe we want to show this geostationary orbit before we go to another other types of what or another orbit, we say that so this is all about geostationary orbit. The geostationary orbit that we say that suppose we have the S surface. This is the S surface. So this is the S surface. So the S surface. And then suppose that this is the equator. So this is equatorial plane. So this is equator. This is equator. And then the geostationary satellites, we say that this is, remember that this is north pole, this is south pole, this is east, this is west. So the geostationary satellites now will be like this. So it's elliptical path. Following the S, if I could have a colored chalk, show it differently. So So remember that this is west, this is east. So this is what we call it geostationary. So this is geostationary satellite. So this is geostationary. Geostationary. Geostationary orbit. And this that the S is surface, yes, north pole, south pole. Can even also have the longitude, the main, we call it the Greenwich meridian. Greenwich meridian. And there we have also number 14 of longitudes. So that's how we sketch the parking orbit. So that's we call geostationary or parking orbit or synchronous orbit. So before I end this lecture, I would like to teach you about another orbit, called the parking orbit. But the difference between the previous orbit, which is the parking orbit or the geostationary orbit, is these types of the satellites or the orbits that I'm going to teach you right now will be revolving. It means that these satellites used to revolve the Earth's surface, but in opposite directions toward the geostationary satellites. So because the geosatellites revolve the Earth from west to east, right? And the satellites I'm going to teach you right now in the next sections before I end this lecture, we call them polar satellites. So they used to revolve the Earth's surface in polar parts of the Earth's surface. When you say polar, this is North Pole and this is South Pole. So the satellites I'm going to teach you right now, they are revolving from North Pole to South Pole, South Pole to North Pole. So these satellites in physics, we call them polar satellite. So say with me, polar satellite, polar satellite, polar satellite, polar satellites, polar satellites, polar satellites. So the primary and fundamental question is, what is polar satellite? What is polar satellite, right? Polar satellite, we say that is a satellite. These also still are artificial satellites, okay? Is a satellite that revolves around the Earth, revolves around the Earth, in the polar orbit. So the polar orbit also is one of the parking orbit, we call it stationary orbit. But the way, when you talk about the polar orbit right now, we are talking about the different compass bearings, so different direction from the geostationary orbits. So this is a satellite that revolves around the Earth in the polar orbit. So polar orbits is the orbit which is at right angles to the equatorial plane. So So you say that polar orbits is the orbit. Okay, so it's the orbit is the orbit which is at right angle. So this polar orbit is the orbit which is at right angle to the equator, to the equatorial axis of the equator. So that's how we define the polar orbit. So this polar satellite passes both north poles and south poles. So the polar satellites revolves S surface. The polar satellites revolves the S surface. Let me write clearly for you. Polar satellites revolve the S in rho, or revolve the S surface so rho was geographical north and the south. Geographical north and south poles. So that's why we call them polar satellites. Okay, so we say that these polar satellites revolve the Earth's surface, okay, through both geographical north and the geographical south poles. So when we sketch, can sketch the Earth as an ellipse like this. Here we have North Pole, or suppose that this is the polar orbit, and then we have the Earth's surface. Have the Earth like an